Yeah.
Okay, it's 4 o'clock. Let's get started. All right, good afternoon, everyone. How's everyone doing today? Hang in there. Midterm, yeah. I know we got one this week too for us too. So hang in there. I know this is really busy time. Okay, so today I think we're probably gonna have a short day. So I just have a couple more examples to do with the spine. I don't really want to start the next thing until we're kind of past the midterm. So today's plan is just to kind of finish up everything with the spine. So I have 2 examples and then just some injuries to talk about, right? So hopefully we get out a bit early today just to give you guys a bit more time studying. One announcement I did want to make. A few people asked me this over the weekend, but the backpack problem on homework 3. So I think it's not stated in the problem, but there's two things there that are assumed to act at the middle of the spine. So if you look at the figure, there's the backpack that kind of comes off the spine, and I have a vector that kind of goes from the backpack up to the weight of the backpack itself. That can be assumed to act halfway up the spine. And then also there's a weight vector that goes down as well. That one also acts at the halfway point of the spine. Okay. So I think it's not stated in fact, I think the figure itself is a little bit misleading because I have these 2 vectors in different places. But you can assume both of those act at the midpoint. Yeah.
So the line that connects to it, that's not perpendicular?
It is perpendicular.
Oh.
But that perpendicular line starts at the midpoint of the spine.
Okay.
Yeah. So actually it might be better if I draw it. So, the spine is like this. The problem kind of gives you a backpack that looks like this. And so in the problem, I give you this perpendicular line like this, right? We'll call this LB. Okay. So this point right here, this is at LS over 2. Okay. So that's the geometry for that. And then the other thing that acts at the halfway point is the weight of the torso itself. Right. So both of those things act at the same midpoint. I think in the figure I kind of drew it where the weight is kind of off center a little bit, but you can assume that both act right at that midpoint. Okay. Okay. Any questions on that or anything else before we get started for today? Okay. All right. So let's go ahead and pick up where we left off on last Wednesday. Okay. All right. So this last section in biostatics that we're going to be talking about before we move on to dynamics is the spine. Okay. So the spine, is very interesting. Not that the other parts are interesting. Everything's interesting in this class. But the part of the spine that makes it interesting is that, even though the spine is meant to be strong, it's meant to be kind of to bear your weight and give a lot of structure. At the same time, your spine is something that's also very sensitive, right? Because the thing with spinal injuries, it's actually quite rare for someone to have what's called an acute injury. So an acute injury is basically something that happens due to one kind of traumatic or catastrophic thing, right? So usually when someone breaks their arm, it's because, they were, doing something crazy, right? You know, spinal injuries are kind of I call them, they're kind of like deaths by 1,000 cuts. And so it's not something that usually happens right away. It's usually kind of the buildup of a lot of bad habits over time. Right? Okay. And so if you remember last time, we did a couple of examples that kind of illustrated the importance of proper lifting techniques, so lifting a load off the ground. So usually you're not going to throw out your back if you lift one box with poor technique. It's just that if you do that constantly, over a long period of time, let's say you're moving from apartment to apartment and you lift all the boxes, from your lower back, you're probably going to be really sore the next day. Okay. And so, whenever you're designing something, that's meant to work with humans, you have to be really cognizant of, what posture people are in and kind of what position their spine is in when they have to do this. Okay. And so for the first example I want to talk about today is I want to talk about workstation design. Because it's really important, especially if you work a job where you have to stand up a lot. So if you have to, you're working in the kitchen, you're working in, any kind of thing that involves manual labor that you're standing up, you want to make sure that whatever you're working on is well, accustomed to, to yourself and your height and to your build and all that stuff. Okay. Even if you work a desk job, I think what you're seeing nowadays is standing desks are becoming a lot more popular. Or desks where you can kind of adjust the height because that it does kind of make a big difference if you're working at your desk for long periods of the day. Okay. Okay. And in particular, we're going to be talking about the height of the workstation. Okay, so let's look at 3 different cases. So in case one, we're going to look at a situation where the workstation is properly adjusted to the person that's working there, right? And so it's at a good height. Okay. So let's say that this person has a job where they're working on something with their hands. It's on a tabletop. Okay. And it's the height of the table is adjusted so that the person can stand up straight comfortably and work for long periods of time. So if you look at his back, you will see that it's very straight, right? So this is a good workstation. Being able to keep a straight back, maintain a good posture is really important, right? And so we kind of spent a lot of time talking about that last time. Okay, next we're going to look at another case. Okay. So let's see what happens when we lower this table a little, right? And so let's say that this workstation is a little bit too small for this person. And so if the workstation's a bit smaller, then to kind of work comfortably, the person has to kind of bend down a little bit. It may not be a lot. And so it may not be something that, you feel right away. It could be something that, you try it out. You're like, oh yeah, this is fun. But, there is kind of a noticeable kind of bend to the person. Okay. So we have kind of an angle to the back, just like that. Okay. Not too severe. So we'll say this is a mildly concerning workstation. And then finally, let's look at a situation where maybe there's no table at all. And so maybe this person is, for whatever reason, maybe there's just not enough budget for a table. And so he has to work on the floor. And so he's basically, maybe he's sitting down, but he has to hunch over quite a lot in order to do his work. Okay. This is case 3. Maybe this person, maybe they're sitting down, but they have to bend over quite a lot to do it. Okay. So you can see that the angle here is much more, much more severe. And so I would say this is a strongly concerning workstation. Okay. So all 3 of these cases kind of have one thing in common. So in all 3 of these cases, the spinal erector muscle kind of in the back of your back, they need to engage in order to maintain this person's posture. Okay. But of course, depending on the nature of the workstation and depending on how much the person has to bend over, the spinal erector muscle may have to do more work in some cases than the other. Okay. Another thing I want you to notice in this situation here that there's no external weight here, and so there's no load that they're picking up. This is just them just standing and just supporting their own body weight. Okay. And so even with just supporting yourself, what you're going to see is that depending on the angle of the back, there's going to be significant differences in how much work the body has to do. And there's also going to be significantly more risk to the spine in certain cases than others. Okay. Okay. Any questions on just the setup for this problem? Okay. All right, so the free body diagram for this problem, it's actually going to be very similar to the backpack problem that we just talked about. Okay. All right, so we're going to draw a spine. We're going to just draw it as a long rod, right? We're going to examine case 1, case 2, case 3 all together because the nature of the forces are not all that different. The only thing that's going to change between case 1, 2, and 3 is just going to be the angle of the spine itself. Okay. So that makes things convenient for us. So we can imagine it all, with the same free body diagram. Okay. And so of course the key parameter here is going to be the tilt angle theta. So we'll call theta, we'll call this the posture. Okay. All right, so let's start including some weights here. Okay. First, we need the weight of the head. Okay, so the weight of the head is going to be right at the end of the spine, so we'll call that W1. Okay. In fact, we'll kind of combine together we'll say this is the weights of the head and the entire upper extremity, so your shoulders and your arms and your hands as well. Okay. Okay. The other weight that we're going to have is the weight of the torso itself. Okay. We'll say that is going to be right here. So we'll call that W2. And so because because we're kind of distributing these weights a little bit more a little bit strangely here. So we're putting the upper extremity together with the head. That kind of shifts the torso weight a little bit closer to the spine itself. Okay. So that's why you see the weight kind of W2 is kind of shifted down more than it typically is. And so normally, we kind of lump together the arms together with the torso. But for this problem, we'll kind of lump it together with the rest of the head. Okay. There's no standard convention for this. And so, just in general, we're taking these kind of distributed masses and we're kind of lumping it together into point masses. Essentially, that's kind of what we're doing. So there's no real standardized way of doing it. And so, some problems you might see me do this, some problems, you may do it otherwise. As long as kind of the net effect is kind of the same in terms of the moments that they create in terms of the overall mass, it doesn't matter all too much kind of where you kind of lump things together. But usually, you want to have usually multiple point masses to, because the weight is kind of distributed all throughout the body. Okay. Okay. Next thing I'm going to put in is the muscle force. And so we're going to put the muscle force right here. Okay. So again, this is the muscle force of your spinal erector muscle. So that's the muscle kind of on your lower back. Okay. And the attachment angle will give it the variable alpha there. All right, and then the last thing, question, yes.
So for W1, because we're combining the head and upper extremity, in theory, we shifted it down a little bit.
It is shifted down. So this is not the entire spine. This may be kind of in the back, kind of below your neck a little bit.
Got it.
Yeah. Mm-hmm. Or right at the neck. That's probably more. Okay, we also need the joint reaction forces, and the joint reaction forces are going to do a little bit differently here as well. Okay. So remember last time when we did an example, we found that the most kind of dangerous force is a compressive force, right? And so the more you're kind of compressing your spine, the more danger you are of hernias and kind of fractures and things like that. Okay. So normally, we split the joint reaction forces into an X component and a Y component, so a vertical component and a horizontal one. But for this one, I'm going to shift it. I'm going to rotate it a little bit, just because we're doing a comparison between the different postures. So I'm going to have one component that is kind of parallel to the spine. Okay. So we'll call this JA. Okay. And then another component that's perpendicular. We'll call that JS. Right. So the A in JA stands for axial. And so if you kind of imagine your spine and your torso is kind of a cylinder. And so the axial direction is the one that's kind of right down the barrel of the cylinder, right? And then S there stands for shearing. So any kind of shearing force that appears. Okay. Okay. And so just like we normally do, we're going to compute. Let's compute the muscle force and joint reaction forces. Okay. But we're going to leave theta as an unknown here, right? And so we're going to plug in different values of theta. And what you're going to see that even with the same forces, that just that posture angle, just changing that is going to make a big difference in the amount of muscle forces that you have to exert and the amount of reaction forces at the joint. Okay. Oh, we need some lengths here too. Let's see how was the best way to do this. Okay, so we'll say that the entire length of the entire spine here we'll say is H. And so the distance from the base of the spine up to where W1 is acting, we'll say that's capital H. And then everything will be defined relative to H. And so the reason I'm doing this is so that, these results will be kind of applicable to a person of any height, okay? So everything is truly good, just going to be a function of just the posture itself. Okay. And so let me define this as point A at the bottom. Where W2 is acting, we'll call that point B. And then where the muscle force acts, we'll call that point C, okay? And so the distance between A and B we'll say the distance between A and B is 0.15 H. Okay. The distance between A and C along the spine is 0.2 H. Okay. And then the overall length, I'm sorry. So the overall length is actually going to be, so H here is actually the height of the person. Sorry about that. So H, height of person. So that includes their lower extremity as well. And so the section of the spine that we're actually looking at here is only going to be 0.3 H. Okay. So the distance from the base of the spine up to where W1 is acting is actually only 30% of H. Yes.
Alpha is a constant, right?
Alpha is a constant. Yeah. Alpha is the angle. So the muscle attachment angle we're going to assume is constant. The only thing that's changing here is the posturing. Yeah. I apologize for that. Yeah. So the overall length of what we're considering here is 0.3 H, and then the other lengths are given down there. Okay. So let's go. Let's solve this like we usually do. So let's go ahead and sum the moments around the spinal joint. Okay. And this is to solve for the muscle force. All right. All right, so remember all the distances that were given in this problem are, distances along the spine itself, right? So they all have to do with the posture. Okay. All right, so let's compute each individual moment from each of the forces. And so let's start with W2. Okay, so since W2 is a weight force always acts vertically. And so the moment arm between W2 and the spine is going to be the horizontal distance between where W2 is acting and the spine, okay? And so the horizontal distance we can see here, right? So between where the spine acts in W2, we have a kind of a hypotenuse length of 0.15 H, okay? And so the horizontal distance of that kind of right triangle there is going to be 0.15 H multiplied by cosine of the posture angle. Okay, so we have W2 multiplied by 0.15 H times cosine of theta. Okay. And now we need the sine. So W2, if we kind of follow it around the joint here, we can see it produces a clockwise moment. And so we need a negative W2. Okay. Our moment from W1 is going to look very similar. The only difference is it's going to be a larger distance. So we have a minus W1 multiplied by 0.3 H cosine of theta. Okay. And then we have the muscle force that's opposing this. And so we have a plus Fm. Okay. Fm is kind of defined in its usual way here, where it's given by its attachment angle relative to the body segment. Okay. So we want the component of Fm that's perpendicular to that line. So we want FM sine of alpha. Okay. And then we're going to multiply that by the distance between where the muscle force attaches and the spine joint itself. And so that's going to be 0.2 H. All right. And so if we see here, every term here has a factor of H. And so since the other side of the equation is 0, we can factor out that H from every single term and divide by it. Okay. So that H is going to cancel out from every term here. All right. And so for the rest of the terms, we can just kind of rearrange them algebraically. And so if we solve for FM from this equation here, we get. So on the numerator here, we're going to have a cosine theta that kind of factors out from both terms. And so I'm just going to pull that out. Okay. So you have a cosine theta, okay, multiplied by quantity, 0.15 W2 plus 0.3 W1 divided by 0.2 times sine of alpha. Okay. So we have an expression here. So, I mean, of course, it's going to depend on the ratio of W2 and W1. But the main thing we have here is the dependence on theta. Okay. Because that's what we're interested in this problem. We're interested in seeing, how does each of these quantities change as theta, goes from 0 to 90. Okay. Okay. So you can see the main dependence here is cosine of that angle, right? And so just like we did previously, let's talk about kind of what are the extremes for cosine, right? And so if we're looking at the range from 0 degrees to 90 degrees, right? That's kind of how we measure the posture. So kind of the worst case would be 0. So for 0 degrees, you're kind of face flat on the ground. 90 degrees is kind of a perfect posture. Okay? Cosine of 0 is 1, right? Whereas cosine of 90 is 0, right? And so this muscle force, what this tells us is that our muscle force here can vary from anywhere between maximum force, when you're kind of face flat on the ground. Well, maybe not face flat on the ground. You're still kind of supporting yourself, but you're as kind of horizontal as you can be, to perfect posture, which is 90 degrees, where, at 90 degrees, you're kind of, your weight is kind of perfectly balanced on your spine. Your spinal erector muscles don't have to do anything. Okay. So that's kind of the difference, right? So we're ranging from, no force at perfect posture to, maximum force when you're kind of down. Okay. All right. So in theory, it is possible to have 0 muscle force, but if you're doing some kind of job where, you're kind of leaning forward to kind of work on something on table, my example here is kind of the best thing. So, even though this podium is kind of, well adjusted to a short person like me, I still have to kind of lean over a little bit to kind of write on my iPad. So it's really hard to have perfect posture all the time. And so realistically, our range here might be from 0 to, maybe 85 degrees. Right? So your muscle force, is probably still going to do something. It's just that, depending on the posture, it may be doing more work than others. Okay. All right. Any questions on this result here? Okay. All right. So let's go ahead and solve for the joint reaction forces. Okay. So for the joint reaction forces, we're going to sum up the forces in our 2 directions. So we're going to have sum of the forces in the axial direction. Okay. So that's going to be the direction that's parallel to the spine. Okay. So in this equation here, we have JA. Right. So JA is the joint reaction force in that direction. Now we need to take each of our other forces and we need to compute its components parallel to the spine and perpendicular to the spine, okay? Okay. So for the muscle force, it's fairly straightforward because the angle that we're given here is already, defined with respect to the spine. Okay. We've already kind of done this many times before. And so we have one component here that's parallel to the spine, right? So this component here is Fm cosine alpha. And we have the component that's perpendicular, which we've already used for the moment. And that's Fm sine alpha, okay? Okay, so let's take the parallel component. Okay, and we can see from this figure here that Fm cosine alpha is going in the opposite direction as JA, right? And so we're gonna have a minus Fm cosine alpha. Okay. So that's our first component there. Next, we need the components for the weights. So this gets a little bit complicated just because of it's not perfectly clear from the figure. Okay, so W1, W2 is going to be the same. So they're both vertical forces. The only thing is we need to get a component that's parallel to the spine and perpendicular to the spine. Okay, so if you've never done this before, it can be a little bit disorienting to kind of make a right triangle out of this, okay? But you kind of need to kind of shift your perspective a little bit. So normally, when we take components of something, right, the vector itself is the hypotenuse of the triangle that we want, right? And so we want to draw a triangle where this W, we want this to be the hypotenuse of a triangle. Okay. And we want to draw it in a certain way so that the two legs of the triangle are one of the legs is parallel to the spine and one of the legs is perpendicular to the spine. Okay. Okay, so let's draw the parallel component first. Okay. So we know the spine is, we know the spine kind of goes like this, right? Where we know this angle here is theta, right? So we know we want one component that's in the same line as that. So let me go ahead and draw one line that's kind of parallel to that. Okay. And then the other component is going to be perpendicular to it. And so, go ahead and take that line that you just drew and draw a line that's perpendicular to it. I think I need to extend it a little bit here. Okay. And the idea is that, when you draw this line that's perpendicular to it, it should meet up with your hypotenuse, right? Because you want to form a right triangle from this. All right, so that's our triangle right there. You can see that this is a right angle right here. Okay. Where this component, the one that we drew first, this is WA, okay? Or the component of W that's parallel to the spine. And then the other one that we just drew is WS. Okay. Notice the directions that I drew these arrows in, right? So we're basically, whenever you separate something, a vector into components, you're basically separating into two vectors that are perpendicular to each other, okay? So if you add, right? So if you consider WA to be a vector, WS to be a vector, you add those two together, you should get your original vector. So you add them kind of tail to head. And so that's kind of why I drew the arrows in that direction, okay? Okay. So all that makes sense, but now the question is, we know that one of the angles in this triangle is 90, right? So that's where the right triangle is. The question is, what is one of the other angles, right? So we need one of the other angles to form our trig relationship. Okay? And so in this situation, we know that this horizontal or the posture that the original slanted line made with the horizontal is theta, right? And so that angle, if you kind of imagine, you start from a horizontal line and you rotate counterclockwise up to where that angle is. Okay. Okay. Now you kind of need to do a little bit of kind of visualizing here in terms of where that angle is. And so that angle there, right? Considering that this is kind of the rotation from horizontal to, horizontal to the posture of the spine, right? This angle is actually the same as this angle right here. Okay. And so how I got that is that, if you consider, you kind of have to like shift your perspective. It's kind of hard when the vector you're looking at is vertical. But remember, this W here is the new hypotenuse, right? This W, you have to kind of consider it to be the same as your original spine right here, right? And so to get into this, configuration, you can see here that we have this WS here is perpendicular to the original spine. And so in order to rotate into that vertical position, you have to go from here and rotate, counterclockwise into that position there. That was a very poor explanation. I know. I'm trying to think of a better way to explain it. It's something that you kind of pick up very visually. You kind of get a lot of intuition from it. And so I think once you kind of see it a few times, you start to kind of really pick it up. But that's kind of how I imagine this, that I have a counterclockwise rotation to go from horizontal to there. I have this perpendicular line that goes from that, and then I rotate counterclockwise to get into that vertical position. Okay. All right. Any questions on that? I know it's a little bit, it takes a bit of time to kind of see it, but once you kind of draw all the triangles, it makes a bit more sense. Okay. All right. So, just trust me. Once you see it kind of a few times, it makes it a bit better. Okay, so let me go ahead and erase some of these lines here, just so we can kind of see. Remember, the whole reason we kind of embarked down this journey is to, we wanted the component of W that's perpendicular to the spine and one that's parallel to the spine. Okay. Okay. And I don't know why it's not erasing. Okay, so for the component that's parallel to the spine, we can see that that's WA right here. Okay. WA. And if we look at our triangle here, we can see that that's going to be W, the hypotenuse, multiplied by cosine of that angle. Okay. So we're going to have a W1, or excuse me, W times sine of that angle. Okay. And then based on the direction of the arrow, you can see it's going down the spine, just like FM. And so we're going to put a minus sign in front of these guys. And of course, all of this is equal to 0. Okay. And so what we have in the end here is we have a fairly simple algebraic expression. And so let's go ahead and solve this equation for JA. Okay. We get JA is equal to W1 plus W2 sine theta plus FM cosine alpha. Okay. Okay. Very long-winded explanation for a fairly simple. All right. So once again, let's look at the dependence of this on theta. And in fact, this axial joint force, this is one that's of strong interest to us, because this is the joint reaction force that's going to compress the spine, right? Okay. So we can see we have a sine theta here, right? So that's one place that depends on theta. Okay. We have another theta dependence because we have FM here, and we know that FM depends on theta by cosine, right? So I'm not going to write the whole FM expression, so FM is actually quite large there, but we know from FM that theta dependence is cosine theta, okay? Okay, So we have kind of two opposite kind of things that are going on here. So on the one hand, we have sine theta. Right? And so once again, let's kind of measure its behavior as it goes from 0 to, well, we didn't say we're not going to go all the way to 90. We'll say 0 to 85 degrees. Okay. So sine of 0, is 0. And then sine of 85, that's not quite 1, but about 1. Okay. So that component of the joint reaction force is going to reach a minimum when you're kind of being punched over as much, but then that component is going to reach a maximum when you're up, straight up. Okay. And that result makes a lot of sense, right? Because that first term with the sine, that is, your weights, right? And so the more your weights are directly kind of aligned with the spine itself, then that weight is going to be supported by your spine bones or the spinal joint. Okay? So that result there makes perfect sense. Okay. But then we know that FM here kind of has the opposite kind of behavior, where we know that the muscle force is going to be maximum at 0 degrees and a minimum at 85. Okay. Or excuse me, the opposite. So it's going to reach a maximum at 0 degrees and a minimum at kind of full, straight posture. Okay. So this is quite interesting. And so, depending on your posture, right, there's always going to be some component of force that's compressing your spine. Right? There's no getting around it. Okay. Now, whether that force comes from, the actual gravity forces of your body weight, or it comes from, counteracting the muscle force, that part depends on the posture. And so we'll see that, we'll see which one is kind of more relevant in the different, once we kind of put in some numbers to this. Okay. All right, any questions on this result here? Okay. All right, so that is the axial joint reaction force. So very quickly, let's do the shearing force as well. Shearing force isn't too interesting. Normally, for a situation where you're just supporting your own weight, normally you wouldn't expect much shearing. But let's compute this anyway. Okay. We'll just do this very quickly. Okay, so we have JS. That's going to be the positive component. We have the two components for the weights. Okay. So that's W1, W2. I'm just going to combine them into one because they're both going in the same direction. Okay. And this is going to be a cosine theta, right? So kind of opposite of what we had for the axial equation. And then we have a minus FM. And then this is going to be sine of alpha. Okay. All this is equal to 0. All right, so once again, if we solve for JS here, we get minus W1 plus W2 cosine theta plus FM sine alpha. All right. So what's interesting here, compared to the axial equation that we have kind of opposite things here. And so we have the weight, the component from the weight is opposite sign from the muscle force. Okay, so unlike the axial component, these two are going to kind of cancel each other out. Okay, so this part and this part, opposite signs. Okay. Whenever you have an equation that has different components with different signs, there's the potential for things to kind of cancel each other out. Okay. Okay. So now that we have these expressions here, let's plug in some values so that we can kind of get a sense of whether the bad posture case really is bad for your back. Okay. Okay, so let's plug in the following numbers. So let's say that W1 is equal to, W1 is going to be equal to 0.18 W, okay? Where W is the weight of the entire person, right? So everything here is based on ratios of this person's weight and height, okay? We'll say that W2 is 0.36 W, okay? We need the attachment angle, which is going to be constant in all three cases. And so we're going to say alpha is equal to 13 degrees. Okay. So these numbers here are applicable for all three cases. Okay. And so the only thing that we're changing between each case is the value of theta. Okay, so for case one, we'll say that theta, remember case one is kind of the perfect posture, or at least as perfect as you can get. So we'll say theta is 85 degrees for that one. For case two, we'll say that theta is 75 degrees. Okay. And then in case three, we'll say theta is 60 degrees. Okay. All right, so it's not that big a difference if you think about it. So between the best case and the worst case, we only have 25 degrees of rotation. Okay, but even just that small rotation there is going to cause a big difference. Okay. Okay, so then let's write out our results. And so let me give you the results in tabular format. Okay, so we have case one, case two, case three. And so for every case, we're going to compute the muscle force. We're going to compute the axial joint force, and then the shearing force. Oops. Okay. So let's do case one first. And so plugging in all the numbers that we have, of course, all the results that we get are going to be relative to the person's body weight. Okay. So for case one, for FM, we get 0.21 W for the muscle force. Okay. For the joint reaction force, we have 0.74 W. Okay. And then the shearing force, it's not quite zero, but it's very close. It's pretty much negligible. So I'm just going to say it's approximately zero. Okay. Okay. So these numbers here are pretty realistic, right? So even if you have the best posture, your spine is still taking up about 75% of your body. Okay. It's not all of it because your lower extremity is, there's a big portion of your body weight in your lower extremity, but still a pretty big portion. Okay. Okay, let's look at case two. So case two, we've only rotated 10 degrees. And so we've only rotated from 85 to 75 degrees. But even just that small rotation is going to cause a big difference in the results. Okay. And so the muscle force that's required for even just that slight rotation is almost 3 times as much, right? So your spinal rector muscles are working 3 times as hard, even for just a very slight rotation of your back. Okay. For the axial joint reaction force, it increases as well. So it goes from 0.74 W to about 1.13 W. So that's about a 50% increase. Okay. Again, 50% more stress on your spine just for a 10-degree rotation. And once again, the shearing forces, it's a little bit further away from zero, but compared to the other numbers there, it's practically still zero, right? That makes sense, right? You're not going to shear your spine just by kind of bending over. Okay. Okay. And then finally, let's let's look at case 3. So case 3 is a bit more of an extreme rotation. So case 3, we have a posture angle of 60 degrees. Okay. And so in that case, the muscle force is 1.2 W, so double what it was in the previous case, almost 6 times as much as the as the good posture case. Okay. And then for JA, we have 1.64 W. So again, that's compared to case 1, that's about twice as much. Okay. And then the shearing force, even for extreme bend, it's pretty much negligible, just because the muscle force and the gravity forces kind of cancel each other out in that direction. Okay. Okay. And so, of course, the two numbers that I want to highlight here are the joint reaction forces in the good posture case and the bad posture case. Okay. So it makes a big difference. So 2x, by itself doesn't seem like that big a deal. But again, if you're doing this, every day, 40 hours a week, 8 hours a day, kind of putting twice as much stress on your spine than you need to, that's going to add up. And so that's going to, create a lot of issues for your spine in the long. All right. Any questions on this? Okay. All right, so that's the last example that I wanted to cover. So last thing I wanted to do before we end today is let's go over some injuries of the spine. Okay. Let me go ahead and share my screen. Okay, so let's talk about some injuries, right? So just like the same way we ended our sections on the upper and lower extremity. Okay, so the most common injury of the spine is lower back pain. And so lower back pain is extremely common. And so if you haven't experienced some in your life already, you likely will at some point. And so about 85% of people at any given time experiences, lower back pain at some point in their life, right? And in fact, fun fact for the US is that lower back pain is the most frequent and expensive of all workers' comp claims in the United States. And so it's so extreme that, I've gone to the doctor a few times in the last couple years, and, you go up to the receptionist and actually the first thing that they ask you, when they look at your age, is like, are you here for workers' comp? I'm like, no, I'm just here for regular checkup. They're like, okay, good. Thank goodness. So yeah, so it's a lot. And, and the source of lower back pain really has kind of evolved too. And so, before it used to be that, if you work some kind of, very kind of labor intensive job, some kind of job that requires a lot of manual labor, likely you're going to come in with some lower back pain. But even now, for people that work, a fairly kind of, a fairly mundane kind of office job, people working from home, that's kind of become a bigger thing too, right? If you don't have, a setup for your office that either allows you to kind of stand up and stretch, or maybe you're not sitting in a chair that provides you with good lumbar support, you're most likely going to cause some pain in your lower back, right? Because just like we talked about, your back is something that it's not something that you just kind of you kind of injure yourself, you throw it out in kind of one big thing. It's kind of the accumulation of a lot of habits and a lot of things that you build up over time. Okay. And these are the kinds of injuries that I think are hardest for people, because if you twist someone's arm, like, yeah, they're going to feel some pain and they're going to try to adjust it. But for something where they don't feel pain immediately, it's very hard for them to kind of correct that. Very hard for them to kind of see that something's wrong unless you have someone that kind of points it out for you. Okay. And so, again, this it can result from either one large load, maybe you try to pick up something, or the repetition of a lot of smaller tasks. Okay. And so the exact cause of pain, there's so many of them. But I think the reason I say here that 60% of cases have unknown origin is it's not that back pain is something that's mysterious that we don't know what causes it. It's not some kind of virus that we're still studying. It's just that a lot of times when people have back pain, it's oftentimes multifaceted. So it's the result of kind of multiple different things. And so it's very hard to kind of pin it down to just kind of one specific cause for a lot of people. Because even if you go into the doctor's office and you have pain and the doctor asks, what do you think has caused this? I think, most people won't be able to give a good answer to that because, even they're not really sure, what's causing it too, right? And so about 60% of cases that go to the doctors, the doctor can't really find kind of pinpoint one clear reason why that pain is occurring. So that's kind of where that stat comes from. All right, any questions on lower back pain? Okay, next injury I want to talk about is fractures. So of course, fractures are not as common, just because you typically aren't sustaining kind of acute injuries to your back, but they are bones just like any part of your body. So they are it is possible to fracture them. Okay. So the most common cause for a fracture of your spine is some kind of catastrophic kind of compressive force on your spine. So a lot of times people experience maybe a very kind of hard blow to the head. And so if that doesn't, damage your skull, all of that compressive force is taken up by your spine. And so that's usually the type of force that can cause a fracture. Okay. So a very acute, very kind of large injury like that. Okay. And, any kind of damage to your spine is can be very, very bad for you just because of its role in protecting the spinal cord. And so if your damage to your spine is so severe that not only does it fracture your spine, but it also, causes severe damage to the spinal cord, you're probably looking at a very, at the very least, a very reduced quality of life. So we're talking things like paralysis or, loss of control of your limbs or worst cases, loss of control of some parts of some of your inner organs. So it can be pretty, severe. And so of course, death is possible as well. Okay. Stress fractures are also common. So if you remember from a previous class when we talked about stress fractures are, basically like fatigue injuries. And so if you are kind of repeatedly kind of putting loads on your spine in a way that kind of, softens up your bones, causes fatigue damage or fatigue cracking, that can happen as well. Okay. And the thing with spinal fractures is because your vertebrae have kind of a complex structure, there's not too much blood flow through your spine, and so they can also be very slow to heal. It's also due to the fact that your spine is kind of almost constantly loaded in some way, right? And so even for the limited blood flow that goes to your spine, it's hard to find. It's hard to rest your spine enough for it to properly heal, because even just standing up or just sitting down, that causes stress and compression on your spine itself. Okay. So it can take people a very, very long time to heal from spinal injuries. And sometimes it requires them to kind of lay in a bed and try to put at least amount of stress on your spine as possible. But of course, if you're bedridden, then that's a big reduction in your quality of life as well. Okay. All right, any questions on fractures? Okay. Okay, hernias. And so we've already kind of talked about hernias before, but hernias are an injury to the intervertebral discs that exist between the different vertebrate bones. Okay. And so remember we talked last time that, in between each of your individual vertebrae, there's this kind of, fibrocartilage, structure called the disc, where its main role is to kind of cushion the compressive forces on the spine. Okay. But if your spine is kind of loaded unevenly, or if there's kind of an excessive kind of compressive force, it can cause kind of this fibrostructural matrix cell structure here to kind of break down, and for that to kind of start to leak out. Okay. Now the leaking itself isn't fine, or is not bad in itself, because that cartilage or that fibrous tissue doesn't really have any nerves running through it. And so even if it starts to leak out, most people won't actually feel it, because there's no way to feel it. The only way that it starts to become problematic is that it starts to bulge out enough so that it starts pinching on your spinal cord. Okay. And your spinal cord is a very, very sensitive, bundle of nerves. And so any kind of, uncomfortable pressure or uncomfortable force on it, you're going to feel it, and it's going to be extremely painful. Okay. And so, a disc herniation could either be caused by traumatic injury, some kind of acute injury, or repeated stress. It's again, kind of like most spinal injuries, it's kind of like a death by 1,000 cuts. And so it's not something that happens right away. Usually kind of that, by repeated stress or by repeated loading, that fibrous kind of structure there kind of starts to break down. Okay. So most commonly, herniations occur at the bottom of your cervical vertebrae. So your cervical spine is kind of near the neck, right? And so your neck kind of experiences a lot of stress, but most commonly it's going to be at your lumbar vertebrae, which is kind of where most of the load bearing takes place. Okay. Question? Yes.
Is hernia just like a way to describe that like leakage, quote unquote? Because I hear people being like, "Oh, you're stressing me out. You're giving me a hernia." Which I'm assuming is not for your spine.
No, yeah. So yeah, the hernia is specifically for this. I've heard a lot of people kind of misuse terms, and so you say, "Oh, I'm getting an aneurysm," right? So you can never get so stressed you get like something like that. It's just kind of I think it's an expression to say like, "Oh, it's causing me a lot of pain that this is happening." So yeah, hernias are specifically for these intervertebral discs that are leaking out and pinching the spine. But I think it's so painful that I think people use it to describe other things too. Yeah. The difficult thing about hernias is that it's often very hard to diagnose someone that's at risk for it. Because again, these hernias they usually don't happen overnight. Usually there's kind of a slow breakdown in the tissue and the cartilage. So in theory, if we had a good way to kind of test someone for it, then we can kind of give some warning signs. But the typical test that people get for kind of bone health and for structural damage is an X-ray. But you can't really pick it up in an X-ray because with an X-ray you can kind of see all your vertebrae, and you can kind of see the space in between them. But there's no calcium in your discs at all. And so the X-ray is not able to pick up your disc. And so if it bulges, an X-ray cannot pick that up. And the worst thing is that, maybe you would think maybe, if you're starting to get a hernia, maybe the distance in between your vertebrae starts to get smaller, right? So maybe a doctor can kind of pick up on that and say, hey, your spinal bones are a little bit closer. Maybe we should get an MRI. Maybe we should look at it. But even for most people, if you get a hernia, the space in between your vertebrae stays roughly the same. And so you won't really feel it until it's kind of too late. Okay. So it's very hard to kind of diagnose someone with it, until they've kind of reached a point where they're in kind of extreme pain. Right? So most treatments for hernias are going to be, on the grand scheme of medical kind of treatments are fairly conservative. And so, with the spine, you typically don't want to go in and operate on there if you don't have to. Any kind of surgical operation carries some risks. So even with the most skilled surgeon, there's a lot of things in your body where you don't really know what it's going to look like until you open it up. And so, most of the time doctors are going to shy away from any kind of surgery on the spine because, they don't want to harm your spinal cord. And so, a lot of times if you have a hernia, there's going to be a lot of physical therapy. There's going to be a lot of, drugs to kind of manage the pain. A lot of maybe like assistive devices to maybe like help your posture, or maybe help you stand up, help you do your work. But only in very, very severe cases, and maybe, and usually there's some other associated injury there. Maybe there's some kind of fracture. That's really the only cases where doctors will opt for surgery. But it's quite rare that they'll do that. All right. Any questions on hernias? Okay. Okay. So the last one I want to talk about, probably you've kind of heard about this injury too, is whiplash. So whiplash is kind of the term that's given, when your neck kind of goes through this very kind of extreme and sudden motion. And so you have kind of a hyperextension and then a hyperflexion of your spine. And so most whiplash most commonly occurs in whenever you get a car accident. And so usually when you're driving a car, your whole body is kind of moving at a certain velocity. And then when you get into an accident, suddenly your entire body will very sharply decelerate. And so when your whole body decelerates, what tends to happen is that your whole body kind of pushes forward, and then your head gets kind of thrown back. And then, and the associated, as your head kind of catches up to the rest of your body, then your head kind of whips forward like that. Okay. So, that's kind of how it occurs, right? So when whiplash occurs, it's basically, you basically have damage to a lot of the bones and a lot of the tissue and kind of the ligaments and the tendons that are in your cervical spine. Okay. And so a lot of the symptoms include neck pain, muscle pain, numbness radiating from the shoulders, arms, and heads, and a lot of times with headache as well. Okay. And kind of the difficult thing about whiplash is that a lot of times, you don't kind of experience the pain or you don't experience the symptoms until maybe like a few days later or a week later. And so a lot of times, people will get into a car accident and then they'll say, oh, yeah, my neck feels okay. But then, a week later and stuff like that, then, maybe that's kind of when you start to develop pain. And kind of the reason for that, I think, is still kind of being researched a little bit. But I think part of it is that, there's a lot of adrenaline that occurs whenever you're in something traumatic like a car accident. And so that may kind of numb a lot of the pain receptors that are there. But also, a lot of these ligaments and tendons and tissues in the neck are not really used to, a very sudden kind of motion like that as well. Automobiles are relatively, recent development in kind of the history of mankind. And so, it's these tendons and ligaments aren't really used to that. And so it kind of takes them a while to kind of realize that they're damaged. And so that's kind of the kind of informal theory, but it's something that's still being researched.
Can you also get whiplash like laterally, like?
Oh yeah.
That way?
Oh yeah, definitely. Yeah. So the most common case is, front to back, but you can absolutely get whiplash this way as well. Yeah. So any kind of damage to like the ligaments and tendons in your neck, from any kind of sudden movement is categorized as whiplash. All right, any questions on this? I think that's it. That's all I got for the slides here. Okay, all right, so that's all I got for today. So we ended class a bit early. So next time I see you guys on Wednesday is going to be for the midterm. So once again, midterm is going to be here in the classroom. So everyone on Zoom, please plan to come here. I'm still working on the exam. I'm hoping to finish it up by tomorrow. There's a big proposal I'm working on too, so I'm trying to get that done. Both are kind of due at the same time. Yeah, question.
Not sure if anybody asks yet, but what's the exam difficulty going to be like in relation to the homework?
About the same. So I try to make if I had to give numbers to it, I'd say the homework would be maybe like level. If I said homework is level 10, then the exam is probably usually like level 8. So about 80% of the difficulty. Yeah. All right. So thank you guys for coming today. Best of luck with studying. So I have office hours today. Today is the last office hours before the exam. So if you have any last questions, come by. If you have questions tomorrow, you can always email me. So that's always available. So yeah, I will see you guys on Wednesday. Yes. Yeah. So 1 8.5 by 11.